I hope you're all rested and ready to go. One more week. Let me briefly outline what I have in mind for the rest of the time. There isn't much. We only have 3 more lectures in which I hope today to cover a little bit more on solids, particularly the conductivity aspect. You won't be responsible for the whole of chapter 37. I haven't really talked about molecules. I think you probably learned a lot about that in chemistry, and I probably can't add much to it, although your background that we added in this course should help you understand things like the shape of wave functions and how when they overlap you might get interesting effects like chemical bonding. I also am not talking about ionic crystals, particularly. They are pretty common, of course, things like sodium chloride, where it seems like the sodium give up their electron, the chlorine picks up an electron, and there's simply an electrostatic interaction, good old Coulomb's law, holding these crystals together. That's pretty straightforward. I think there's nothing too much conceptually new there, so I skipped over it. The more interesting aspects are, I think, how we distinguish the materials that are not obviously molecular nor ionic. Things like silicon, things like copper. Why do they differ one from the other? Why are they so different? So I think we'll have to go to something a little deeper, namely electronic energy levels, to try to understand that. I would point out to you that this was a complete mystery going back 100 years. Namely, this was sort of figured out in the 1930s, why some materials are metals, some are silicon is sort of a semiconductor. And it's only about 50 years or 60 that we gained control over semiconductors, such that they're now the backbone of the electronics industry. And we even have a valley named after silicon. So we've come quite a long way in about 50 or 60 years. Now, the other thing I want to talk about today, if I can get to it, I hope we will, is the beginning of nuclear physics. And you'll be having a lab on that. You're supposed to do certain preparations, like sign off, that you're going to be safe in the lab. It's not dangerous, but you want to be especially careful handling radioactive materials. And we will talk about that here. So that would be part of it. I just want to introduce that today. And on Wednesday, I'll finish up the story as far as we're going to do. We're not going to do everything in every chapter because we just don't have time. And I'll skip chapter 39 entirely. That is to say, the particles to cosmos, the subnuclear particles, like and string theories and all those kinds of things. That might be fun. In fact, I think the truth of the matter is you have enough background now. If you're interested, you could read that chapter and get an appreciation for what it says. You really don't need me, and you'll get a nice impression of what's going on in those extremes, which are actually very active fields in physics these days. The idea of this recent announcement of the Higgs boson, which is, again, a subnuclear particle, and then all the interesting work that's going on in astronomy these days, the cosmos. Things like searching for planets outside of our solar system and all those things. A lot of which is going on at Berkeley. There's Professor Marcy here, who was one of the first to discover planets. It's very hard to do. How do you see a planet near a distant star? It's very tricky, but they can do it. And then they're even able to discern sometimes whether the planet is solid or gaseous, and whether it even has an atmosphere, and whether, they keep thinking that they're going to discover whether there's life on other planets. So that's a big issue now. You can read that in chapter 39. It's entertaining, if nothing else. And people like to talk about things like black holes and all those far out things. Indeed, far out, astronomically far out. Again, I can't help it. But anyhow, I just want to make sure that you have a clear idea of what is conductivity. Oh, and then let me finish with the sort of schedule. That'll be Wednesday. Friday, I thought I would just come in and have sort of a review of the whole course, just to put everything in place. There's a homework due tomorrow in the evening. That'll be a little bit on nuclear physics. And that'll be it for as far as homework goes. I'm going to hear a cheer? Okay. All right. So we'll have a review on Friday. From my side and your side, you can bring in questions. By now, you should be able to hold things a little bit together. Then, of course, the week after that will be the triple R. Yes, ma'am. Yes, I'll have a practice final probably by the end of this week. And on that, the idea is, look, the course is built up from the very simplest thing, Coulomb's law on day 1, to now where we use Coulomb's law in Bohr's orbits and so on like that. So it really has accumulated, and even if I talk about modern physics, you're relying on the classical physics to understand it. So the course will, the final exam will cover, in principle, emphasize the last third of the course because you haven't been tested on that. So that we have a 3-hour exam. You could say maybe 2/3 of it will be on the modern physics, but in a way, modern physics includes classical physics as its base. So you really have to know that stuff too. And then there'll be some other parts which will be specifically on the classical first 2/3. But that'll sort of be like the last third of the exam, sort of cumulative thing. It's all mixed together at this point, so it's really hard to say what is what. But we'll try. I hope by now you'll have a pretty good feeling for what physics is about. Oh, and so next week, I will have review sessions personally. I'll have my regular office hours. That'll be Wednesday and Friday. And on the times of the lecture, we'll have this room again. And anybody who wants to can come. We'll have just a review session from 3 to 4 on Monday, but not, let me make it clear, not 3 to 4 on Wednesday, because I have to go to a conference and leave about that time. So, but I will have an office hour from 2 to 3. Yes. If you want to come and talk about that. And I think the GSIs will organize review sessions, and you can go and talk to them, and there'll be office hours for them as well, which will be posted. Well, all this will be posted, so you won't have to remember it. But I think you'll have plenty of time to review and to practice. Hopefully that answers temporarily some of the questions. Okay, well, I just wanted to make sure that we understand, for starters here, just a little bit more about conductivity, electrical conductivity, which is so important an idea, and just the very simple idea of resistance and resistivity. You see, you may have dealt with, and we have dealt with, just objects which we call resistors. This is an object in which there's a material inside a little pill, or it could be in very many different kinds of shape, but it's the resistance in ohms of a particular object. Now, the concept that we want to have is, if you have a material, how do you compare one material to another in its ability to carry current? Just to carry current. Something specific about the material. Now here, it's just a particular object. So what we try to get at is the concept of resistivity. by the way, I probably mentioned this before. When you see IVITY at the end of a word, usually it's trying to refer to the intrinsic properties of something, as against resistance, which is of a particular object. Object. In other words, in a way, sometimes we call that an artifact. It's a particular resistor. But this doesn't tell you what the resistivity is. So when you have an ivity property, you have to define what you mean. And in the case of resistance, it's pretty obvious. If you look at the formula for the resistance of an object, it's rho L over A. Right? That's our typical formula for the resistance of an object, where L is the length of it and A is the area. So we define the resistivity as the resistance of a block of stuff, which is 1 square meter by 1 meter long. So its area is this, and its length is 1 meter. So if you put that in here, the resistance of a block, these are all in metric units, so it's R, and if you have a length of 1 meter, and you have an area of 1 meter squared, a block like that will have the resistance equal to the resistivity. So what we're saying here simply is that anytime I want to say compare aluminum with lead, I make a block of aluminum 1 meter squared by 1 meter long, and I make it of aluminum, and then I can compare it to an equal block of, say, lead. And I know that I'm really comparing apples to apples here. It's the same shape. So, well, in fact, you probably wouldn't make a block 1 meter squared by 1 meter. You'd probably make something much smaller, but then you'd scale it up to a meter by a meter. But what this is really saying, I've chosen a standard something, and then I get the specific quality that I'm after, because I'm comparing things when I've specified what I'm comparing to what. See what I mean? So for another quality like that is a density, you see, as compared to the weight of something. See, the weight would be the weight of a particular object or artifact. But it doesn't tell you much about how dense whether it's got a lot of stuff in it. It's just telling you weight. But a density is specific. It's the weight, again, per unit volume. So it's per unit something. So resistivity is the resistance per unit something, and the unit is a cubic meter of stuff in that shape. By the way, it has to be that shape, because if you take that shape and you distort it, in other words, you could take that shape and make it the same volume, something like this, it'll have a very different resistance, right? If I took a cubic meter and I stretched it out to something like that, it'll have a very different resistance, right? Because what it counts is the area and the length. So you got to be a little careful about that. So just want to make sure you have that concept, okay? So it's a specific resistance of a specific shape. And you'll come across, and probably in your scientific work and other things, I come across things like emissivity and emittance, ivity and enhance, and you'll come across it. So resistivity is one concept. So that's how much a thing like this would resist flow. The other concept is the conductivity, which is the amount, the reciprocal of this. And by the way, the units of this are in, let's see, so resistivity has units R, and you have meters squared and meter. Meters comes across, so it's ohm meter is the units. Ohms times meters. Okay. Now the conductivity, people describe materials variously, either by the conductivity or resistivity. Maybe if you're a positive thinker, you think of conductivity, and if you're a negative type of thinker, you think of resistance. In any case, usually the formula for conductivity is quoted more often because it's it's a little more visualizable what's going on. Why would a thing conduct well? Well, the thing that you would expect, and in fact the formula is Ne squared tau over m, which we can derive if you like, but you could see where this is a sensible formula in the sense that it says the more carriers I have, this is the number of carriers per unit volume, the charge, that's reasonable. Tau is the mean free time that is between collisions with the material. In other words, if the electrons do not, or the charge carriers do not collide often with the material, then the electrons pick up speed. Because as that demonstration we once did, the rolling ball rolling down the plank with the needles in it, the nails in it, and there were collisions as it goes down. The longer it goes before it has a collision, the faster it'll pick up speed. And then it collides and the speed stops. And then if it has a long path time, it picks up speed due to the electric field that's applied. Because the conductivity is related to the multiplied by the electric field will give you the current density, that is the amps per square centimeter. So this is a very reasonable thing. And inversely is the mass, because if you put a field on, you'll get an acceleration, but the more inertia the thing has, the less it will pick up speed. So you would expect it to be inversely as the mass. So that's a pretty reasonable formula, and it should be aware of it. I'll leave it up there because we're going to see in various materials why they have different conductivities depending on the different parameters. And well, E you can't do much about. The charge carriers pretty much have charge E. But what we can play with are the charge densities, N, and we might be able to play with the collision time between collisions of these moving particles. Indeed, in fact, the mass you would think is not something you could play with, but it turns out that there is something called the effective mass. And inside a material, things don't always look like they have the same mass as they have in free space. But I won't worry about that right now. But the thing that you should be aware of here is that it's really amazing what a variety of conductivities there are. Well, here they give it in terms of resistivity. There's many, many orders of magnitude between, say, a semiconductor and a metal conductor in how well it conducts or resists electrical flow. And that was a puzzle that people were faced with, when they discovered all these different kinds of materials and started passing currents through them. So the question is, how do we understand this? And the answer came out of quantum theory, where we took the ideas very, very quickly. I'll run through it. Namely, we start out with atoms, which have quantum energy levels. Again, due to their being waves held within an atom. I keep going back to that because it's a great idea. the electrons are held within an atom. They have these various shapes, and you have these various energy levels, which are the energy levels fitting in to, let me get my arrow here, why not? If I, so we fill up these energy levels, the 2s, the 1s, the 2s, the 2p, 3s, 3p, 3d, etc. These are in the isolated atom. And I think we showed in some demonstrations of when you bring atoms together, their wave functions overlap. And that gives you energy levels close by each other, which are resemble the original atomic energy levels, but they're spread out into what we call a band. Actually, if you look at what they're trying to show here, is that there's extremely close energy levels, which are due to all the atoms in the whole crystal. They all contribute an energy level to this band. And the way a charge moves is if it's in one of these levels, if you put electric field, it might pick up energy and move to higher and higher energy levels, and if they're close enough by, the electric field can make it go up and up to higher and higher energy, and we call that a conducting electron. So we would call a band like here a conducting band, whereas a band like this, which is totally full, is like a highway with a traffic jam. It's complete, all the cars are parked in here, and nobody can move. But if you have empty lanes up in here, an electric field can make that electron move up and up among these very closely spaced levels, and you have mobility of the electron in a conduction band. So that's the basic idea. Now the question is, if you have a particular element, does it develop closed bands, or does it develop open bands? And that's where the details matter. Some cases are very obvious, and others are not. For example, a case that is obviously a good conductor is something like lithium, where you have, it's got 2 electrons in the 1s state, and has 1 electron in the 2s state. Now, this state can hold 2 electrons, this 2s state can hold 2 electrons, but lithium only has 1. That means it's got only 1 electron in this band, and so it's got a lot of empty lanes to run in, and so lithium is a very good metal. On the other hand, if you would fill up a thing up to this level, which would be the first of the noble gases, where you fill up the 2s and the 2p, you fill all those, there, you filled up to this level, and there's a big gap to the next one. So electrons in this band here would not be able to move. In fact, that would be, what would be the first one? Neon? The first noble gas. Whatever it is, neon, krypton, one of those. Xenon. They would be closed, and they're very unreactive, right? Helium even, like this would be helium. Very unreactive, and they would form insulators, obviously, because they fill up a band, and there's just the next higher level is way high, so you don't get any conduction. So some cases are obvious, like those two. The one end, the alkalis and the rare gases, those are obvious. But in between, you have to think. You maybe turn it over to a very smart theoretician. And they did. And we've got a lot of answers. But in any case, we can classify things as an insulator if the gap between where the electrons fill up a band to where there's empty lanes up here, if that is very large compared to the energy provided by heat, then there are no electrons in this band, and this is an insulator. So you have things like diamond, where I think this energy gap is around 10 electron volts. On the other hand, you have some cases where, in the case like silicon and germanium, where the energy gap is not 10, but more or less like 1. And then it's a little closer. You have a certain little probability of getting the heat to drive an electron out of this state into this state and allow for conduction in this conduction band. Or you could have the case of a metal, where like sodium or potassium, potassium, you would have the electrons filling half a band, makes for a very good conductor. Or it could be that at some higher level overlaps this one, and this one being empty, the electrons can run around in this upper band. That can happen too. That would be a little more complicated case. The more simple cases are these, namely cases where you have an insulator, you have a filled band with a big gap, or a conductor where you have just a band which, does not have enough electrons to fill it, and so the electrons can run up into these states here very freely, and you have a good conductor. So there's no energy gap for electrons in the conduction band. Okay, so you can read this. I really don't want to spend too much time on it. But I just wanted you to be aware that, I think I talked in the last Friday's lecture about this, namely that the semiconductor, because the energy gap is relatively small, you can play with it a little bit, and we can control it. Even though this might be too much for many electrons to jump across by heat alone, what we can do is put impurities into the silicon, impurities being well chosen. For example, if we add, now silicon is in the group 4, the same as group as carbon, and so it has 3s squared, 3p squared. So it's a group 4 element. What you can do is you can put in elements from groups 3 and 5 into replace the silicon, which normally bonds to 4 other silicons in a kind of a diamond structure, same as carbon, diamond carbon. But if you replace one of the silicons with one of these other elements, let's say a group 5, you see the group 5 element will have 4 bonds like silicon, but then it has this extra electron because it has one more electron. And that electron, it turns out, has a very weak binding to this. This might be arsenic or antimony.